Okay, I'm recording now.
I have a question, Dr. Higgins.
Yes.
In question number 4, are we assuming that the rod will not start swinging?
The beam or
The beam, yeah, that the beam will not start swinging.
I don't think that that is a wise assumption.
Okay, thank you.
Yep.
Like at the instant that that cable breaks, what motion is happening?
I think a better way to think about it, honestly, would be to try to figure out what this thing is going to look like at two different instances, and see whether I'm actually going to walk through each of these like this. I would try to think of what it could possibly look like at two different instances, and then draw a reference frame on the body that's connected to like the center of mass of the body, or roughly where you think the center of mass is. And then in the second instant, if that coordinate system rotates, you know the body rotated. Or if that coordinate system translated, or only translated, you know that the body only translated. So I would kind of consider it two different instances. And the reason I say that is because acceleration is extraordinarily hard to visualize for a single instant, because it involves a change in velocities over time. Maybe another minute or two. just for the sake of time, let's go ahead and come back together. So tell me what you think for number one. What type of motion do you think this plate G is doing?
I chose general planar.
Okay, very good. And why did you choose that?
So there's pure translation as it moves along uh with the roller, but if the roller is going really fast, then it's gonna lag behind
Yeah.
because they give us inertia.
Yeah. So this is kind of like the problem of having something dangling from your rear view mirror. Once your car starts to move, it's gonna start swinging back, right? Because it's got some inertia. So yeah, once A starts moving, it will be translating forward, but it also has this likelihood of rotating backwards. So if we draw another point in time, A might be here, and this Dorito hanging on is probably going to be doing something like this. So if I were to maybe draw a coordinate frame here, and I look at it at another time step, that coordinate frame has both translated and rotated. Okay, very good. Tell me about number two, body BGD. Pure translation. Interesting. Some people get this one mixed up with fixed axis rotation, but it's not. So this object, there's no opportunity because these are like rigid links holding it to the ceiling. There's no opportunity for one side of this object to be any higher or lower than the other side. Right? So B and D are always going to be at the exact same height, which means this thing can only be translating. So we could draw this at another point in time, maybe up higher. And we would have this guy. We drew a reference frame here, reference frame here. We see that that frame has not rotated at all. It is only translated. So this is pure translation. Okay, number three. Perfect. Yep, we can't tell. So if A is slipping relative to the larger cylinder, then this cylinder is likely just sitting in place and rotating about a fixed axis here at the center. That's all well and good, but if these two surfaces are maybe rougher than we expected, and A grabs onto the big cylinder, there is a possibility that that cylinder gets flung out into space. Okay, and in that case, we'd be doing what? General planar motion, right? It's probably rotating and translating through space. Okay, so we can't tell. Number four. General planar motion, you said what? Fixed axis.
Because as it breaks, it still has inertia about the center of gravity. And so as one pulls down, it's going to pull this side this way. So it's going to cause it to swing.
Yes. Yeah, okay. So let's think about fixed axis rotation. I can see where you're coming from. You probably, where did you think the fixed axis was? At A. Okay, so let's think about what's happening then. If this beam falls, this center of mass is going to go whoosh with a good amount of velocity, right? That's going to cause this entire thing, like with the beam hanging on the end here, to rotate this way. Right? So is this axis, is that axis fixed? No, it's not fixed. Yeah.
If it was like a steel beam at A instead of a rope, would that be fixed axis and the rope at A couldn't move?
Yeah, I think so.
If this could not move, if it were fixed like this, yes, that would be fixed axis rotation. Yeah. Yeah, I would call this general planar motion. Yeah. So the other question then becomes once it's rotating with these two things, is it then fixed axis rotation about the pivot at the top? No, because these two things can rotate relative to one another. That's why it's still not fixed axis rotation. So this is general planar. And actually, we saw an example of this in class. If you accidentally grab the general planar motion equations, what happens if it's something simpler? Things go to zero. Now, if you choose a simplified form of the general planar motion of the general planar equations, and you ignore the fact that other types of motion are happening, that's when you get the problem wrong. Right? So if you choose the fixed axis rotation equations, but it's actually doing general planar motion, that's an issue. But if you choose general planar and you do it right, you can still get the problem right. Okay. All right, number 5. Yep, it's fixed axis. Yeah, because the axis at A never moves. Number 6. Acceleration of the plane, the normal reaction. Yeah, I'm thinking general planar because the plane can both move forward and rotate about anything.
Yeah, but it says the lift.
Sorry.
No, it is.
Yeah.
Yeah, I thought it was pre-lit.
Well,
Yeah.
I would still go general planar because, oh, is it pre?
If we're looking at it horizontally, I thought it was just translation.
Oh,
There's
yeah,
Let me read more carefully.
I think he's right.
Yeah, there's
It says there's no lift caused by the
Low
wings.
velocity- Low velocity neglect any lift caused by the wings.
Initially, it take off the ending for that determining the acceleration of plane reactions on the moves of each of the two wheels. Okay, so it's pure translation. Yeah, you're right. We can't rotate because it's telling us specifically that the plane is still stuck on the ground. Good catch. Number 7.
General planar.
Yep, although actually there might be,
Maybe pure rotation too, because I don't miss.
But
Yeah, if there's zero friction, then it's just
still-
fixed axis.
yeah, so because it asks determine if the disc slips, there is still the possibility that it could be doing fixed axis rotation if it's just slipping in place. I think this is one we can't tell. But in general, if it's not slipping, if it were not slipping, what would it be doing?
Both.
General planar.
Yeah.
Yeah, if it is slipping, it might not translate forward at all. It might just rotate in place, like if you're sitting on a block of ice. All right, 8. What's the crate doing? Yep, your translation. If we raise this 4-bar mechanism up here, the platform is still flat. You haven't rotated. Nine.
Fixed axis rotation.
Yep, it's just weird because it's not a circular object. And 10.
I really can't tell until it's a fix. But it's still good.
Um, yes, I think you're right. I think we would need to know if it slips.
My argument for general planar was that we know that there is some friction, so we know there has to be some amount of translational movement. So I put general planar. I actually put impossible without calculating slip, but after looking at it again.
So tell me this then, Samuel. What if, without calculating our friction, what if the friction force ended up being perfectly equal to P?
Well, it can't be because we have a mu.
It could be. The mu is mu Kn. Right? The friction force equals mu Kn or mu
Sure.
Sn. And without calculating the normal force, we don't know what the friction force is. So there's still without calculating anything, there's still the potential that the friction force is somehow equal to P. In which case it would just be, yes.
Like why?
Well, what does P
if
stand
that's
for?
General planar, even if, like, I don't think we need to know the slip, because if it pulls, it's gonna rotate even like. Because there's still some force acting on it. Even if it slips, it's still a force acting on it, causing it to move and rotate at the same time.
Not if there's an equal and opposite force. It won't translate. You can be rotating in place without translating if your forces cancel each other. They create a pure couple.
But if it's the ground, no.
I don't care where it's coming from.
Oh,
If you're slipping with respect to the ground has no bearing. Other than the friction force that it applies. Okay. All right. But as we said, if you apply general planar motion equations, you still have the chance of getting it right. All right. So let's look at two work through problems. One is going to be an absolute motion analysis problem, and one is going to be a relative motion analysis problem. And I believe that both are shorter than anything I did in class. Which I still need to finish that problem and upload it.
I hope so.
Yeah, it was kind of complicated. Okay. Let's talk the absolute motion analysis problem. And again, I'll give you, we have until 11. Give you maybe 10 minutes to work on this on your own, and then I'll do 5 minutes to write it up myself. So at the instant shown, theta equals 60 degrees, and rod AB is subjected to a deceleration of 16 meters per second squared when the velocity is 10 meters per second. Determine the angular velocity and angular acceleration of link CD at this instant. Help me really quickly so we're all on the same page. Help me find out how to write. Actually, first let's play a little bit more of motion classification. There are 3 different objects here, and all 3 are doing a different classification of motion. Can you tell me what each one is doing? So for instance, tell me rod AB. What's that doing? Beautiful. What's another one? Yep, BC's general planar.
CD fixed axis.
Beautiful. So what can sometimes happen? Let's pretend you tried to apply the general planar motion equation to CD. If you don't recognize that certain things are 0, what'll happen is you end up with too many unknowns and not enough equations to solve your problem. So we still do need to be good at recognizing when something is doing fixed axis rotation, so that we have the right number of unknowns. Okay, so what are we being asked to find? Can I write that in math? Determine the angular velocity and angular acceleration of link CD at this instant. How do I write that?
and like A is C.
How do we do angular velocity? What symbol do we use? Omega. Omega CD. And what CD? Alpha. Alpha CD. Good job. it's also going to be important to recognize one other link, that omega CD is going to be equal to theta dot. Right, they give you a theta here. And we know that angular velocity is a property of the body. Right, so if we define it between any one point in the body, that's the angular velocity of the entire body. So theta here defines our angular rotation for the whole body. We can also write alpha similarly. Okay, so my next question is usually, how do I get from the area of the problem where I'm given a bunch of information about, how do I relate that to the part of the problem that I'm being asked about?
Go point to point.
I could go point to point, but let's think carefully about maybe the first point to point I would consider. The first point to point I would consider is probably, well, it looks like it's giving me information about point A, but this body is doing pure translation. So why does that matter?
It's giving us information about point B as well.
Absolutely, yeah. So all the points on this same rigid body are doing the same velocity and same acceleration because it's only doing pure translation. Okay. And then it turns out I don't actually need to care too much about part body BC. I can actually just analyze what's happening to X here, because I can write X as a function of thetas. Okay, so I'm gonna maybe write out in words. How can we relate the motion given about rod AB to the motion of CD? Well, if I write out an expression for X, I'm going to care about the velocity and the acceleration of point B, which I've been given in the problem statement, and I have to consider these thetas. So X is going to relate the two quantities I care about. So I'm going to do this via the time derivatives of X. All right, now I'm going to shut up. Y'all go from there and try to figure it out. find yourself really, really stuck, please ask questions. Okay, let me come see you where.
Slide.
Right expression for x that includes theta. So, in fact, tell me, is velocity of x related to the velocity of theta? How are they?
Okay, so you.
Okay, yeah, so like ignore the latest for right now. How are AB and x dot related? You see it now? So that's why it's important, because it allows us to relate E to those thetas. And those thetas are basic, the time derivative of those thetas is what the concept is for. So, do some trig to write an expression for x and how it's related to theta and some of those distances as well.
Yeah, no, I'm not doing this right. Is there more than one way to solve this problem?
Most likely. No?
Yeah, look at it. It's no, it's, yes.
Beautiful.
I mean, for being a kid, it's not very different. Or is it as long as it's consistent?
I would draw more.
Okay.
So that.
Which direction?
Okay, yeah, that makes sense.
So the way the problem is written, it's telling you that the velocity of AB is always 10 meters. Well, okay, no, it's not always, but don't assume that just because it reaches the point B reaches the corner.
Yeah.
In fact, you don't need to know anything.
Alright.
None of that's pertinent.
Right.
So the first thing you should start thinking about is try to write x. How is it related to a? There's some trigs.
But like, right, so it's both the side, like, I'm trying. They're definitely trying.
And so if you take dx dt, how is that related to the velocity?
From just one point to no.
Every point on the rod is moving at the same velocity.
Okay.
How is dx dt related?
Yeah, you can draw your.
The speed at which that gap gets bigger is the exact same.
Speed at which we're doing it now.
Yeah.
So lengthens every time it pulls up.
Yeah, okay, so that is like.
Government is
equal,
so
right?
yes.
Alright.
That would
Guarantee
be
I'm
equal. So, this quantity X, this distance between D and B, that is the exact same
I know a
thing,
lot.
or the time derivative of that value
Normally.
is equivalent to the velocity of wave.
Oh. Oh, I mean.
No, write your expression for X. I told you, write an expression for X as it relates to theta. Use your trig. That's your fun.
That's the unique one, yeah. Okay.
But after he told me how he did it, I felt like I was cheating by just like going, it's, his way is the right way,
Okay,
but I'm.
see if you get the
persevering.
same answer, that'll be interesting.
I'm very stuck.
Get stuck?
Yeah.
Okay, let me do the very first step that we should do. Samuel, or did you say you're stuck?
Yeah, I'm trying to. Yeah.
Okay, so my very first piece of advice, or what, there's kind of two things here. One is we have to be able to recognize that dx dt, the time rate of change of this gap, is equivalent to the velocity of B. Like, that's the definition of B, is how fast is this gap getting bigger? Okay. And velocity of B, how is that related to velocity of A? They're the same. Okay, velocity of B equals the velocity of A equals dx dt equals what I'm given in the problem. Okay. Now using trig, I can write an expression for x and how it depends on theta. And then I can take a time derivative of that. So let's work through it together. So first thing I've been asking you to do is draw the trig problem for how x relates to theta. These are thetas. Oops. What do they have themselves? That's a theta. These are 300 millimeters. This quantity up here is x. Okay, so if I wanted to write x as a function of theta, I could say, oh, these look like two right triangles here. And this quantity of this right triangle is just what? Okay, it's x over 2, sure. But how do I relate it to theta and 300? Just this section is 300 cosine theta. Okay. One thing we should be careful about, though, is that in the rest of the problem, our velocities are given as meters per second and acceleration as meters per second squared. So I actually want to go ahead and change these millimeters to meters, just because it's meters everywhere else in the rest of the problem. Okay, so this is going to be 0.3 meters. Okay, and x is just two of these quantities. We agree with that? Okay. What happens if I take a time derivative? Yeah. Yep. Okay. X is written here as a function of theta, not as a function of time. So I can't immediately take a time derivative of it. I have to be very careful to apply chain rule. What is dx d theta? Derivative cosine is so minus 0.6 sine of theta times theta dot. And this is equal to velocity of point B, which is equal to the velocity of point A, which is equal to what I'm given in the problem. I'm given in the problem, actually, now I want to be careful about directions. Maybe we'll say that X is to the left, Y is up. Okay, so V here is 10, positive 10 meters per second. Okay, and then it says, at the instant shown, theta equals 60 degrees. Find angular velocity. Whoops. So if theta equals 60 degrees, find angular velocity. I think angular velocity is the only unknown in this equation. I should have 10 equals minus 0.6 sine of 60 times theta dot. I can solve for theta dot. That's what it's asking me for. Okay, so we should get theta dot equals I believe it comes out. Hold on. As positive 19.245 radians per second. Huh? Doing pretty good. Okay, how do I find acceleration? Take another time derivative. Very good. So if I do d squared x dt squared, I need to take another time derivative of this. That looks like a product rule. So I'm going to have to do the first times the derivative of the second plus the second times the derivative of the first. Right, the derivative of the first is another chain rule. So that the derivative of the outside is the derivative of sine should be cosine. So minus 0.6 cosine theta times theta dot. Okay, this is the acceleration of point A, or the acceleration of point B, or the acceleration of the rod AB, which is minus 16 meters per second squared. Theta is still 60 degrees. Theta dot we found in the previous part of the problem. Okay, the only unknown left is theta double dot, which is the same as alpha, CD. Okay. So I can solve for alpha. So this is minus 16 equals minus 0.6 sine 60. I can even plug this in if I wanted to. solve for alpha, we should get 183. I'm curious, where did you get with your long version?
Didn't finish.
Didn't finish. Do you think it was possible to do it that way? Or do you not have enough information?
I wanna say yes, because I would've. Ideally, I, would've solved for the angular velocity, of BC and then just like inverted it to CD, but using like systems of equations, so like I would line all that. And then use systems of equations to solve for all of them.
You,
Missing my one missing variable, which was,
I think you might have had to recognize that by the symmetry of the problem, omega BC is equal and opposite to omega CD. I think you'd have had to recognize that.
yeah,
If you left them as like not related to each other, you might have had too many unknowns.
no, there we go.
Yeah, I know.
Okay.
Yeah, okay. You probably could have gotten there. Okay, we're running out of time.
Isn't theta dot negative 19?
Sorry, go ahead.
Isn't theta dot negative 19?
That's what I got as well.
I'm getting confused on the signs. The book had it as clockwise 19.
Degree per second.
Which should have been positive. But that's not what we're getting. So the way that we did, okay, so the way that we did this coordinate system by assuming X is to the left and Y up, if you do right hand rule, that puts positive Z into the page. Right? So I'm not sure where I messed up on signs.
So it's counterclockwise or clockwise, like on the actual?
The book said that it should be clockwise 19.24 radians per second, but if that were the case, then we should have gotten a positive theta dot. We could also think about it as,
Because as your log goes out, it's going, so it should go up.
no, we could do it visually. So if AB is moving to the left, then these things are getting further spread out. And so CD was here, like down here, and it rotated upwards, which is a clockwise rotation.
Oh, we're looking at CD.
Yeah, we're being asked about CD.
So
So regardless of whether we got a positive or negative, we can by visual inspection tell that it should be, like, as long as AB is moving to the left, which we know because they have an arrow pointing to the left for 10 meters per second. We know that CD must be rotating clockwise. I'm seeing some I don't believe you faces.
So is
Yeah.
theta.
Oh, sorry.
The logic
Behind that
Why?
reasoning. Yeah.
Why do you get X? Why do you create that equation and why you do that? How would you know to get certain things out of deriving that?
So why start with writing an expression for X and then finding a time derivative of it?
How do you know where to start?
So there are multiple ways to solve the problem.
your cousin's name.
No, it's my brother's name, Andrew.
Yes.
So Andrew's first thought was, let's use our relative motion equations to take what I know about the velocity of point B to write some expression for the velocity of point C. And then do the same thing to relate what I know about the velocity of point D related to the velocity of point C. That is probably one way that would have worked. However, the way that I did is likely simpler, and it depends on you recognizing that that this quantity x, if you write it out based on the trig, it gives you a direct relationship between the velocity of point B here and the rate of change of these thetas. Right, so you're always looking for how to relate what you've been given to what you're being asked about. And x is that link, right? The time rate of change of x is the velocity of B. But I also see this trigonometric relationship to relate it to how CD is rotating, which is what I'm being asked for in the problem. So recognizing that there's a direct link between what I'm being given and what I'm being asked about, that's why I think I should write an expression for x that relates these two quantities. And the only way to get it in terms of a velocity is to take the time derivative of x. Okay. Okay. Yeah, we have 5 minutes. We're not really gonna get to be able to do this one all the way. But I do think it is a good problem to work on. So what would you prefer? Would you prefer I walk you through it, and then after the fact you can use it as a study problem and you can try it first and then look back at my solution? Or would you rather me give you 4 minutes now to attempt it?
I have a question about the last problem.
Still questions about the last problem? Okay.
Yeah, they want us to give the vector quantities of omega and alpha.
They don't make that very clear, to be honest.
Okay. Would we just say in the u hat theta direction or something?
No, I would say that they're in the k hat direction.
Sure. Yeah, that's correct.
So either you can say it's in the k positive or negative k hat direction, or you can just draw the direction of motion.
Okay, thank you.
This arrow.
Thank you.
They all achieve the same thing.
I'm sorry.
You're fine. You're totally fine. Okay. We have negligible time. So I'll just write out the solution, and if you want to review this problem later, you can. Okay. All right. So if rod AB slides along the horizontal collar with a velocity of 60 feet per second, determine the angular velocity of link BC and the velocity of point C at the instant shown. So I'm given. Oh, and then the problem, I didn't appreciate the problem statement. They really should tell you that points O and C form a horizontal line. So those are perfectly horizontal to one another at the instant shown. And you'll need to know that. All right, so I'm given that I'm being told about how this object that's doing pure translation, I'm told about its velocity. So I think I'm gonna have to know something about the velocity of point B. So I'm gonna go ahead and write down my given is that the velocity of B equals minus 60 I hat. And I'm being asked to find omega BC and the velocity of C at the instant shown. Okay, so my first thought here is that I know an expression where I can relate the velocity of B to the velocity of C because they're attached to the same rigid body, BC. But it turns out that's not going to be enough information. I'm going to have to do this trick where, again, I say point C is shared between two rigid bodies. So I wrote how B is related to C, but I can also separately relate how point O here is related to C. I'll end up with two different expressions for the velocity of C, and I can set them equal to each other to solve for my unknowns. Okay, so this object here, what type of movement is it doing? You think it's doing fixed axis rotation. Where's your fixed axis?
Right, you said.
CB. CB. Yeah, OC is doing fixed axis rotation for sure. CB is doing general planar motion. Okay, so we'll just have to be careful about that. All right, so my first thought is to relate points B and C, which are on the same rigid body. And so I get that velocity of C is equal to velocity of B plus omega BC cross R C slash B. Again, this would be given on your equation sheet. And now is a great time to start figuring out where it is on your equation sheet. Shoot, I forgot there's another class after this. Okay. Let's see. Okay, so I can write velocity of B is given to me in the problem. That's minus 60 I hat plus omega BC is what I'm being asked for, so I certainly don't know what it is. But this is a two-dimensional problem, so that I know it goes about which direction. K hat, yeah. Omega BC K hat. And then RC slash B is the position of C with respect to B, which I can draw as a vector as the position of C with respect to B, so it goes this way. And I have enough information in the problem that I can go ahead and do the trig on this vector. So it should be minus 2.5 cosine 30 I hat plus 2.5 sine 30 j hat. Okay, this isn't enough information. The reason I know that it's not enough information is because I have one unknown here, but I also don't know the components of VC. So I have a VCX that goes in the I hat direction and a VCY that goes in the J hat direction. So really in total I have two equations. I have an I hat equation and a J hat equation, but I have three unknowns. Right, so I'm screwed. I can't solve this. So next I want to write another equation. Hey, I'll get out of here in just a second. Relating points O and C on the same rigid body. So velocity of C equals velocity of O plus omega OC K hat cross R C slash O. Is O, point O, is that moving at all? Nope, that goes to 0. So we just get omega cross R, where R is the vector that goes to C with respect to O. So it goes this way. Should be positive 0.5 I hat. Okay, now I'll have an expression for VC here and an expression for VC here. And I can set them equal to each other. I'll end up with two unknowns, omega BC and omega OC. But I'll have an I hat equation and a J hat equation, and I can solve two equations for two unknowns. And that's how I solve this problem. Okay. When I upload the notes, I'll have this problem completed. Okay. All right. Thanks, everybody. Sorry we ran out of time, but great job asking questions today. Thanks, everyone online.